I am going to demonstrate the use of Parasoft C, C++ tests in the analysis of safety critical C, C++ projects. I'll be using the example project here, and I have a compiler. So we will be doing static analysis, dynamic analysis, and see some code coverage metrics, including MCDC. First, the project must build. To load this project into the Parasoft Eclipse-based IDE, we need to generate a BDF file. To generate the BDF file, we need to run the Parasoft utility called CPP test trace. Let me clean the project to bring it to its clean slate. When I build the project, I type make or whatever, followed by whatever options after that. To generate the BDF, you prefix that command with CPP test trace, okay, followed by whatever you need to pass to make. What happens here is it forms a parent-child process tree. Make is a child. When make spawns compilers, such as GCC, C++, or cross compilers, the parent CPP test trace via an LD preload technique intercepts fopen and other POSIX calls such as execve. Because of this, everything make does is visible to CPP test trace. With known compiler executable names like GCC and G++, it can identify and collect the list of C and C++ source files participating in the build. So I'll press enter. The BDF has been generated. By default, CPP test trace recognize popular compiler executable names, GCC, G++, Clang, and others. The BDF text file looks like this. You can see the compiler options passed, and most importantly, the participant C and C++ files are listed now. With this BDF file generated, we will launch the IDE CPP test. Parasoft is a plugin to an Eclipse-based IDE. Eclipse operates by creating a workspace. We are asked to create an empty workspace. In this location here, I decided to use the same name to my project to tell me which workspace corresponds to which project. I will load the BDF via create project from a build data file. And here, the compiler family has been auto-detected. My C, C++, and linkers have been auto-populated. In cases where auto-detection fails, then you will have to drop down and select manually the matching compiler family for your compiler, and then paste the C, C++, and the linker executable. You can review the compiler family settings by clicking the stop node, go to Properties, Parasoft C++ Test, Build Settings. An initial successful static analysis run can tell us if our initial compiler family configuration is the right one. I can select one file to statically analyze this one file, or I can select the entire node to statically analyze all files of the project. I'll just choose to statically analyze using effective C++ static analysis rules. Go to Console tab to see if there are error logs in this process. We are now at 45% in our static analysis. Effective C++ static analysis has successfully finished. 54 tasks reported. Double-clicking on a reported violation will lead you to the location of that violation. If you need more information, you can right-click and view rule documentation. Can generate a report. Report formats could be HTML, PDF, SARA, XML, and others. I'll choose HTML. Effective C++ mostly consists of pattern-based static analysis rules. The other category of static analysis rule is what you call the flow-based. Let's try that. That's using static analysis, flow analysis standard. Violations in a flow-based analysis are presented in a stack frame format to trace the flow of root cause. Such as this one. Violations detected in one file could have a root cause in another file in bank.cpp. So flow-based analysis spans across multiple files if necessary. So they are reported in stack frame presentation. Now all of this is native unit testing. We compile and execute on the same machine in my laptop. What about for the scenario that involves cross compilers? So let me close this, and I will switch to my other terminal. We will use the same project, demo Eclipse. So I will clean the changes that we did here. And now that we are back, in this cross-compiler demonstration, I will use this cross-compiler ARM64 7.5.0, and our target is inside a remote location box. Is running ARM64. So I will cross-compile this project by changing the makefile. First, I will check that it builds. It produced an ARM64 binary, which I could not run here because we are in an x86 64. So it builds. I'll make clean. So we have a makefile that we made a change ready for cross-compilation. It is time to generate a BDF. Just like before, I can type cpp test trace and then make. It runs fine, but the BDF is not generated. Reason is the cross-compiler name, this one, falls a little bit outside of the recognizable pattern by CPP test trace. In cases like this, we need to help the CPP test trace by specifying a regular expression so that it can capture the compiler invocation. So I'll run again the make and then add is the option here. So this regular expression captures GCC, G++, and LD. Sorry. Now the BDF file has been generated. Just like before, it was able to capture the participant C and C++ files during this build. With the BDF generated, I will load again the BDF in the IDE. So I'll create another workspace name. And auto detection of the compiler family failed. In this case, you need to drop down and select the matching compiler family. And in fact, the populated forms here is also incorrect. In this case, I need to manually make this adjustment. Let's try to do a static analysis for sanity check. Go to Console tab to monitor for error messages. Static analysis has completed. Now let's do unit test. First, I need to auto-generate test cases. Just like before, these cases have been auto-generated. At this point, I cannot run unit test because I did not introduce our target. Let us recall that our target is, let me open a terminal here. Target is box. The IP is this one. You will also notice that I configured my target with passwordless SSH using private public key. If you need to type for a password, then a dialog will ask for it. So knowing the IP of my target, I need to make an adjustment to run unit test. We can recall that we executed run unit test, but this is only for native testing. There is a template for situations where the target is different. Go to embedded systems, and that template is this one, run test for targets with SSH. If your target requires serial communication instead of SSH, there is also a template for that. It is very flexible. So run test for targets with SSH. I will duplicate this. It will appear under user defined. To avoid confusion, I will put my, and then I will click execution. Here, I will specify the IP address of the target, the user, the home, and the user. There is no password here, but you can expand this menu item. It is fully flexible using the insides of the XML. For coverage types, you can select edit, and by default, it only has line coverage, but you can enable more like decision, MCDC. And then to explain a little bit of how this works, you can select the test execution flow, and this is an XML script. The contents of this XML are steps that you are already familiar. Every developer are doing this on a daily basis, such as SCP, such as SSH, when you sys mode, execute, and then SCP again, copy back the results to your laptop. So to summarize, these are the steps that embedded developers are doing. They are wrapped under a custom step. Yes, you can create your own custom step here. You can edit this as free as you can. If the target is accessible through serial communication such as POTI, then it's up to you. For example, you can use OpenOCD to transfer the firmware. So it depends on your target. So now that that is explained, and I also showed you the place where you can enable more coverage, I will save this and close. The target is now properly introduced. It is time to run cross-compiled unit testing on target. Right-click, Parasoft, test using user defined, as we have a user defined configuration this time. Embedded systems my run unit tests for targets with SSH. Let's check at the console log to see some steps in action. This is a minor issue because we are using a Windows machine 132. So let's go back to configuration. And because of the min GW that I'm using here, so go back here and go to execution, symbols, remove the save stubs. Apply, close, and run again by clicking this arrow here. So we are now cross-compiling and executing in target. And here it is. As usual, our code coverage reports is in the coverage tab, but there's a lot to learn from the console tab here. I will scroll up to show that during cross compilation, some Parasoft provided runtime participates in your firmware. This one. Okay, scroll this over and analyze what parts of Parasoft source code participates in the cross compilation and joins your firmware. So this is the instrumented phase. Of course, you can generate a report from this run. And this is the result of our cross-compiled on-target execution. We can SSH into the target. And we can see the test exec. This is the cross-compiled firmware that just happened right now. In fact, I can manually run it here. And then I can see that these two log files have been generated. These two log files are copied back to the laptop and code covers are computed. So watch carefully these two log files. If I go back to the IDE and go back to the disk configuration, this one. So we deleted them upon exit here, RMRF. So that's why they were lost there. And this log file also got copied into your workspace location. It became basis for code coverage metrics. That is it. The basis flow of how to use Parasoft C++ Test Professional in analyzing safety critical C and C++. While what I showed here is driven by the graphical interface with enough configuration, everything can be driven in the command line without needing of a graphical interface. In that case of a pure command line, configurations will be in properties file and reports will be in the HTML file. Thank you.